In the last video, we computed the determinants for three matrices. If you take a look at these three matrices, you might notice that these are in fact the three matrices that you need to implement all of the row operations for Gaussian elimination. So we know that the replacement operations can be encoded as either an upper or lower triangular matrix. So if we want to add B times row 2 to row 1 of a 2 by 2 matrix, then we encode this using the upper triangular matrix 1, 0, B1. And if we want to add C times row 1 to row 2, we can use the lower triangular matrix 1C, 0, 1. We can also scale any of our rows, either the first row by A or the second row by D, using a diagonal matrix. And finally, for interchange, we simply interchange the first row and the second row of the identity matrix. Now, for the replacement operations, we remember that these matrices have determinant 1. The two scaling operations, the first one has determinant A, the second has determinant D. And finally, the interchange operation has determinant -1. The main tool that we'll use for this video in computing general determinants is the following theorem. The determinant is a multiplicative function. That is, the determinant of A times B is equal to the determinant of A multiplied by the determinant of B. So to see how this is useful, let's work an example. So let's start out with the matrix A with entries 1, -2, and -1, 2. We can start out first by performing the replacement operation, add twice row 1 to row 2, which we encode as multiplication on the left by the lower triangular matrix with columns 1, 2, and 0, 1. Now, we have a matrix whose columns are 1, 0, and -1, 0. So we make an observation, namely, the second column is -1 times the first column. If we think about these two vectors, which make up the columns of our matrix, they lie on the same line. So of course, if we revert back to our geometric definition of the determinant, we can see that these two vectors don't really form an actual parallelogram. They really only give us a line. And a line is a one-dimensional figure, which of course does not have area. So the determinant of this matrix, which we've called A1, is 0. If we use the theorem, then we observe that we can write the determinant of A1 is equal to the determinant of our lower triangular matrix multiplied by the determinant of A. Since we know that the determinant of A1 is 0 and the determinant of our lower triangular matrix is 1, we see that the determinant of A is 0. For a slightly more complicated example, let's take the matrix A with columns 2, 2, and 1, -1. We can, of course, row reduce this matrix. We'll first take row 2 and subtract row 1 from it. Next, we'll scale the second row by -1/2. Our third operation is to subtract the second row from the first row. And finally, for our fourth operation, we will scale the first row by 1/2. So we start off by observing that we can write the identity matrix as the determinant of the left-hand side, which is the identity, is 1. We can compute the determinant of each of the four matrices on the right-hand side. The first one is 1/2. The second one has determinant 1. The third one has determinant -1/2. The third one has determinant 1. And the fourth one has determinant, whatever determinant of A is. Multiplying the right-hand side together, we see that 1 is equal to the determinant of A divided by -4. So if we multiply both sides by -4, we get that the determinant of A is -4. In general, if you have a 2 by 2 matrix whose entries are A, B, C, D, with a little bit of work, you could show that the determinant of such a matrix is AD minus BC. For general n by n matrices, our observations extend exactly the way you would expect them to. So the matrix that encodes the row operation replace row I by row I plus A times row J has determinant 1. The matrix that encodes scaling row I by A has determinant A. And the matrix that interchanges rows I and J has determinant -1. So for example, if we wanted to compute the determinant of the 3 by 3 matrix, 1, 2, 3, 2, 5, 6, 3, 6, 11, and we would start out by putting this matrix into reduced row echelon form. First, we'll replace row 2 by row 2 minus 2 row 1 and row 3 by -3 row 1. Next, we'll scale row 3 by 1/2. We'll subtract 3 times row 3 from row 1, and our fourth and final operation will be to subtract twice row 2 from row 1. Now, to save a little bit of space, we can name these matrices that we use to implement the row operations. I will name them E1, E2, E3, and E4. So we have written down I is equal to E4 times E3 times E2 times E1 times A. So of course, in order to compute the determinant of A, we compute the determinant of each of these matrices one by one. The determinant of the identity matrix is always 1. Our fourth operation was a replacement operation, which has determinant 1. Our third row operation was also a replacement operation. That has determinant 1 as well. Our second operation was a scaling operation. We scaled the third row by 1/2, so that has determinant 1/2. And our first operation was a combination of 2 replacements. Each of those replacements has a determinant 1, so when we multiply them together, we get the matrix E1. That determinant is also 1. So if we multiply both sides of this equation, then we'll see that the determinant of A is 2.